Question 2. A particle moves in a straight line so that its position x centimeters relative to the origin at t seconds is given by x equals t squared minus 12t plus 11, where of course t must be equal to or greater than 0. In part A, we're looking at finding the initial velocity. Now, if x of t is defined as t squared minus 12t plus 11, then we know the function describing the velocity is simply the first derivative, and therefore it's defined as 2t minus 12. Moving on to B, when does its velocity equal 0, and at what is its position in time? So to do this one, we grab our velocity function, and it's asking us when is this going to be equal to 0, and to do that we simply set the left hand side to 0 and then simply solve for t. And what we find is that t is in fact equal to 6 seconds. Done. Alright, actually no, not done. We have to find the position at this point in time as well. So using this value of 6 here, we sub it back into the function describing the displacement, and that's going to be 6 squared minus 12 times 6 plus 11. This is going to come out as 36. Take 72 plus 11. And then looking at this, it'll be negative 36 plus 11, and that will come down to be negative 25 meters. So in the context of it, what is its position at this point in time? It is 25 meters to the left of the origin. Alright, nothing too tricky yet. Now in part C, it's asking what is the average velocity for the first 3 seconds. Now if we visualize this function here, v of t equals 2t over 12. So if we visualize the function here, x of t equals 2t or t squared minus 12t over 11, then what we find is that if we visualize this function, what we're going to find is it's going to look something of the likes like that. And the starting position is going to be somewhere up here, and the t equals 3 seconds is going to be down there. And what we're finding is we're looking for the average velocity, so that's the change in distance over the change in time. So what we're expecting is some sort of line here, so it's an average. Now this is pretty messy, so if we go across the Desmos, we can observe what's going on here a little bit easier. So if I type in the function, s of t is defined as t squared minus 12t plus 11. What we're looking at is the points at t equals 0, so 11. So let's just type that in a little bit nicer. Okay, at 11 or at 0. So here's 0 and 11, and then at 3 seconds. So here, now if I plot that in, what we find is that it forms a straight line between there and there. And the question itself is, what is the average velocity? Well, it's simply using the 2-point formula to find the slope of this particular line here, and it comes out to be -9. How did I know how to do the slope? Well, it's simply asking for the average, and we're simply applying the formula. We're simply going for the formula rise over run, and effectively that's going to be it was f of 0 minus f of 3 3, and by f I mean s. And then it's going to be 0 take 3, and hence the reason it comes out to be negative, let's say, negative 9. And that will be centimeters per second. So average speed. Average velocity, sorry. Alright, question D, determine the average speed for the first 3 seconds. Okay, so looking at that, it's a case of we're going for average speed is a case of distance over time. Now you might be tempted to simply calculate the displacement of the particle at 3 seconds, but the downside is that the particle itself, or if you do this, then you're going to get its displacement from the origin and not necessarily the distance it's traveled over that point in time. What I mean by that is at at x of t, it's defined as t squared minus 12t plus 11. And if we go for the initial condition of when t equals 0, what we find is that it equals plus 11. Now at 3 seconds, when it's asking for the first 3 seconds, the location of the particle is going to be at 3 squared, 12 times 3 plus 11. So that will be 9 minus 36 plus 11. And that will come out to be 20 take 36 and then negative 16. So what we find is that at the initial condition of 0 seconds, it's 11 centimeters to the right of the origin, and at 3 seconds it's 16 meters to the, or centimeters to the left of the origin. Now if we draw a motion diagram, so I just do a rough sketch of one here. If we set this to, this will be x of t. If we set this to 0 and we set this to positive 11 and therefore this one to negative 16, what we find is that at t equals 0, we're over here, and that t equals 3, we're all the way over here. And the distance traveled is the distance of this line here. So the distance itself is going to be 11 plus 16, and that's going to come out to be 27. And therefore, using this formula up here, the average speed is going to be 27 over 3 seconds, because we're starting at 0 and we're going to 3, and therefore it's going to come out as 9 centimeters per second. So that's how we do question 2. Not too hard, just a little bit vexing when we get to C and D. Now going down to question 3. A particle moves along a horizontal straight line starting at point O. The position/time graph for the motion of the particle is shown to the right over here. So have a look at some sort of parabolic function there. So for part A, it says, for which values of t is the particle stationary? Now, what does that mean? Well, it's a case of when is it not moving? Now, we don't have a function to work with here, so we're just going to have to work with the graph. And looking at the graph, this the y-axis is displacement, and this one is time. So when the particle is stationary, it means that its displacement won't be changing. So what we're going for is looking for the stationary points. So this point here, and the stationary point here is at x equals 2. The particle is stationary, and therefore, for which values of t is the particle stationary? Well, the particle is stationary at t equals 2 seconds. Part B, for which values of t is the particle moving to the right? So this is a case of thinking about how is the value or how is the displacement changing, and what we're doing is looking at the displacement or change in displacement with respect to time, or displacement with respect to change in time. So we're going for the derivative here. So if the stationary point is here, think about what's the slope on the left hand side, and it's going to be positive. Slope on the right hand side is negative, and therefore what we find is that if we take the derivative, we're going to have something that looks like that. So the question is, for which values of t is the particle moving to the right? Well, when we're having positive velocity, we're moving to the right. When we have negative velocity, we're moving to the left. And therefore, looking at the graph here, when we have a positive slope indicating a positive velocity, t is less than 2. So we're going to go t is less than 2. Notice it's not less than or equal to. And remember the constraints of the graph as well. The domain, t cannot be less than 0. So I'm going to put down 0 is less than t is less than 2. The reason being at t equals 0, the velocity is at 0 as well. Actually, no, it should be that. That's better. So 0 is less than or equal to t is less than 2 because we're looking at up here. Alright, now question C. How far from the origin does the particle go to the right? So again, we don't have the formula, so we have to infer the information from the graph here. How far does it go? Alright, so it's a case of when is the velocity 0, in which case when is it going to hit its maximum displacement from the origin, and it's all a case of here. So how far does the particle go to the right? It goes, we go across, and it's going to be that guy there. So it's 8 meters. Part D. How long does it take to return to the origin? Well, okay, if it's at its maximum here, how far across? What's the x value from here to here when it hits the origin there? And it's simply 4 take 2. And that's going to come out as 2 seconds. Okay, E. The position of the particle x in meters at time t seconds is given by the rule of the form x equals p t squared plus qt plus r, for t is greater than or equal to 0. From this graph, determine the values of p, q, and r. Alright, so we're getting our displacement function defined by pt squared plus qt plus r, and we find that t is greater than or equal to 0. So effectively find p, q, and r. So what we've got here is 3 unknowns, and therefore we need to build 3 equations to find the unknowns. Now, simply looking at this, think about it. If you know, you can solve it 2 ways. You can take the derivative and look at the stationary points, or it's a little bit easier than that as well. You don't even need to go for the derivative, but rather look at the roots. There's a root here and here, so you know that x of t is going to equal 0 when t is equal to 0 and t is equal to 4. So you're able to build 2 equations from that. And you're also able to build an equation from x of t equals 8 when t is equal to 2. So this point here. So what we can do is we can use these values here to build all of our equations. What we find is we don't actually use calculus for this one. So let's we'll grab these so I don't forget. Move them down here. And building the equations, what we're going to do is we'll go for this 0 first, and by this 0 I mean this 0 here, and we're going to go x of 0 is going to equal p t squared plus qt plus r, and when that's when t is equal to 0, the left hand side equals 0. And the reason I chose this particular value is because I could see by putting in these values here, what would end up happening is that everything will get cancelled out except for the r, and the r would be revealed to be simply 0, which simplifies our equation down to x of t is going to simply be p t squared plus q t. So nothing to it really. In fact, it just makes it a little bit easier. Now we use the next 2 points, this guy here and these guys here, to synthesize 2 more models which will reveal the values of p and q. So going for the first one, the 4, we'll go 0 equals p 4 squared plus q 4. That's going to come out as 16p plus 4q, and I'll divide both sides by 4 so we can reduce it down to 4p plus q, and we'll call this model 1. Now going for our second model, we're going to use this guy here. So x of t is going to equal 8 when t is equal to 2. Dividing both sides by 2. Easy. So now we've got 2 models and 2 unknowns. Using the process of elimination, this will become 0 minus 4 is minus 4. 4p minus 2p is going to be 2p, and the q's get cancelled out, and therefore p is going to be equal to simply -2. Grabbing this value here of p, so if p equals -2, then we can go 0 equals 4 -2 plus q, and therefore q is going to equal 8, and therefore our model x of t is going to equal -2t squared plus, not q, but rather 8t. Done. Looking up for now f, find the velocity of the particle at t equals 3 seconds. So finding the velocity, we're going to go v of t is simply the first derivative of the displacement. So 2 times 2t plus 8, that's going to come out as 4t plus 8. And then, whoops, we're going to say 3 seconds. 4 times 3 plus 8. And remembering that was a negative, this is going to be -12 plus 8. And therefore, our velocity at 3 seconds is simply going to equal 4 meters per second. Too easy. -4 meters per second. So it's moving 4 meters per second to the left at t equals 3 seconds. Yep. Alright. Now going down to question 4. The position of a body moving in a straight line, x centimeters from the origin at time equals t seconds, is given by x equals 1 over 3 t cubed minus 12t plus 6. Find the rate and change of position with respect to time at t equals 3 seconds. So that's a case of going x of t is a third t cubed minus 12t plus 6. It's simply asking the rate of change in position. So it's a fancy way of saying what's the velocity at t equals 3. So again, going for the first derivative here, we're going to get t squared minus 12. And then we're going to throw in when t is equal to 3, because the question simply lacked the value 3 here. And 9 minus 12. And therefore, the velocity at t equals 3 is equal to minus 3 meters per second. So it's moving 3 meters per second to the left at t equals 3 seconds. Now, part B, find the time at which the velocity is equal to 0. So it's a case of saying, well, if our velocity function is defined as t squared minus 12, what values of t will the velocity equal 0? So it's simply a case of solving for t. So in this case, we've got t squared equals positive 12, and therefore t equals the square root of 12. And then simplifying this answer here, what we find is that if we simplify this, it will be 4 times 3, and then 2 root 3, and that's seconds. Right, so the velocity is equal to 0 at 2 root 3 seconds, or you can throw that in your calculator and simply write it out as a decimal. If you put in that value there, if you stop there, that would be adequate. If you went down to here, that would be also adequate. And if you did something like, I can't remember off the top of my head because I don't have a calculator, but if you did x point blah blah blah, then that's also fine. Alright, so moving down, question 8. The position x meters at time t seconds, where t is greater than or equal to 0, of a particle moving in a straight line is given by x equals t squared minus 7t plus 10. When does its velocity equal 0? So if x of t is defined as t squared minus 7t plus 10, this is our displacement function, then our velocity function is going to be the first derivative, so it will be 2t minus 7. And so when does the velocity equal 0? Well, if that's the case, we need to set our left-hand side to 0 and then solve for t. And what we find is t is equals to 7 on 2, which is the same as equaling 3.5 seconds. So the velocity is 0 at 3.5 seconds. B, find the acceleration at this time. Alright, well, if v of t is equal to 2t minus 7, v of t is going to be the first derivative of velocity, or the second derivative of displacement. So we're going to go a of t is simply equal to 2, and therefore this is a nice easy one. Our acceleration at time 3.5 seconds is simply equal to 2, and what we find is that it's actually always equal to 2, so nothing too complicated to do there. Now for C, find the distance traveled in the first 5 seconds. Now this is where we can get ourselves into a little bit of bother. Notice that in part A, we discovered our velocity becomes stationary at t equals 3.5 seconds, and the function defining the displacement is a quadratic. So what that is suggestive of is that the particle is going to move in one direction, and then it's going to stop and start going in another direction. So we need to account for the particle doing something like that. Now, to determine or to account for all of these factors, what we need to do is we need to use our displacement function, and we need to find three parameters when x is 0. So the displacement at 0, we need to find the displacement at 3.5. The reason for 3.5 is we know that's when the particle is stationary, and that's when we're going to see a change in velocity or a change in the movement, direction of movement. And then we need to find the displacement at 5 seconds, because that's the time that it's asking for over here. So getting all of these values, let's move it up so I can see the equation. We're going to go, well, first one's going to be plus 10. It's simply a given, grab that guy. Second one is going to be 3.5 squared minus 7 times 3.5 plus 10. And then the third one is going to be 5 squared minus 7 times 5 plus 10. And I'll quickly whip out my calculator and put those in. Alright, so using my calculator, I've used Desmos in this case. I've calculated the displacement at all of these locations. So at 0 it's 10, at 3.5 it's negative 2.25, and at 5 seconds it's at 0. So negative 2.25. And this one is 0, so nice and easy. So what we find is that we're in positive, then we go into negative, and then we flip back around and go to 0. Now, to do the distance traveled here, what we need to do is to take into account a motion diagram. And we've got to account for a 0, we've got to account for a 10. I'm just going to sketch this because we only want to see the trend of what's going on. It doesn't have to be too accurate. And then minus 2.25. And this is, question defines it as x of t. Alright, awesome. Now at t equals 0 seconds, we're at 10 meters from the origin to the right. So we're going to be, do a different color. Let's go purple. We are at t equals 0 seconds. Then at t equals 3.5 seconds, we're all the way over here. And then at t equals, where are we? 0 seconds, not 0, 5 seconds. We're over here. So the motion of the particle can be described like this. Moves from the right to the left. Then at t equals 3.5 seconds, it spins around and it goes back over here. So it's a case of what's the total trip distance? Well, this part here is going to be 10 plus 2.25, and then up here it's 2.25 to the right. Just check the question again to make sure I'm doing the right thing. Find the distance traveled in the first 5 seconds. Okay, so the distance traveled is going to be 10 plus 2.25 plus 2.25, and that's going to come out as 10 plus 4.5, and therefore distance traveled is 14.5 meters. Remember, it's asking for distance, so that's a scalar value, hence the reason why everything's turned positive. We're just looking for the length of this line that we've just drawn. Alright, now in part D, when does its velocity equal minus 2 meters per second, and what is its time in that position? So grab the velocity function, which we defined as 2t takes 7. And it's asking when does the velocity equal -2. So simply set the left hand side to -2 and solve for t. So I've got to add 7 to both sides here, so that's -5 to t, and therefore t is going to equal negative. It's not going to be negative, it's going to be positive 5 divided by 2. Therefore t is going to be 2.5 seconds. So at 2.5 seconds, that's what it's going to be. The velocity is going to be -2 meters per second. Having a look at that on Desmos, we can visualize that in Desmos by grabbing this function here, going d over dx equals that d over dt. That's going to be our function describing velocity, and then it's asking when is it going to be -2. Well, we discovered that was at x equals 2.5. So -2 there, 2.5 -2. And therefore, if we look at where this line cuts, it's at -1.25. So its position is going to be at -1.25, showing that algebraically, of course. Our function describing the displacement is t squared minus 7t plus 10. Simply throw in 2.5. And it's going to come out as -1.25 meters. So in which case it's going to be 1.25 meters to the left of the origin, consistent with what we observed with this graph over here. So this has been a video on how we can solve some of these questions.